Today I'm going to present our approach for the Miracle project. So this is a joint work with Puxian Yu and my PhD advisor, Professor James Allen. So we are from CIIR at UMass Amherst. So here's an outline for my presentation. First, we're gonna quickly go over the Miracle task data and baselines. Then I will introduce our model building pipeline. And finally, I will show some result and draw the conclusion from our solution. So the task of Miracle is, I would say, very important and also straightforward, right? Information access should not focus only on English, and in general, advanced AI systems should not become a kind of privilege for English speakers. So Miracle focused on the monolingual retrieval across a wide range of languages. From the data perspective, compare with other multilingual retrieval datasets such as CIIR matrix, multilingual and Marco. The Miracle data have three advantages. The first one will be the broad coverage of the languages, including both high and low resource languages. And the second is the human annotated labels with rich relevance judgments, which means for each query, we have multiple relevant documents. And third, as Miracle provides an entirely new set of test queries as the test B set. So these nice features make Miracle an ideal data set for evaluating multilingual IR systems. So besides data, Miracle also come with three baselines, the BM25, the MDPR, and the hybrid. So we noticed that by combining the BM25 and MDPR, the hybrid baseline actually has 88.9% of the recall at 100 documents. So because of this reasonably good recall, we choose hybrid as the initial ranking method and focus on the re-ranking step. So here is an overview of our model building pipeline. Basically, we build a bi-encoder and a cross-encoder re-rankers following different steps and using different data sets. Next, I will talk about each model and each step in detail. I will mostly focus on the bi-encoder with the cross-lingual distillation here. So let's talk about the bi-encoder model. We follow the Colbert architecture to build a bi-encoder teacher model. So let's first call it a teacher model here. Then we use the XMR Roberta to initialize the weights of the encoder and use the same scoring function, which is the token level max similarity operation from Colbert. For training, we use the data from MS Marco triples and use the cross entropy loss function to train this Colbert model. So now we have a multilingual bi-encoder retrieval model. So theoretically, it can be applied to any languages, or I would say any language that covers by the XMR. However, because MS Marco is in English, right? The retrieval knowledge learned in this model is mostly trapped inside the English tokens. So next step, we'll use this model as a teacher and to build a student model towards a certain language. So our goal is to transfer the retrieval knowledge in English to the target language. And we call this step a cross-lingual knowledge distillation. So before I go into the details, I want to remind us of very important facts of the Colbert scoring function, that it is permutation invariant, which means given for example, given three tokens here, we get a ranking score S1. You may want to shuffle this in any orders. For example, 3, 1, 2 here, you get a ranking score S2. According to the Colbert scoring function, S1 equals S2. So this nice feature, so given this nice feature, for now, we can ignore the scoring function and consider the model as a general text encoder. So we want to have a student model that behaves like the teacher model, which means given a pair of parallel inputs, the student model in target language can generate token embeddings that are similar to the teacher model in English. For example, here, given an English sentence and its corresponding sentence in Swahili, we want to find a way of mapping Swahili tokens to the English tokens. So we have our high-level goal, right? We want to token embeddings from the student like the token embeddings from the teacher. So in another word, to guide the training process, we need a token alignment between teacher and student. So we convert the task of finding the token alignment as the optimal transport problem. So here is an example to explain the optimal transport problem, which, suppose you have a source and a target place. And in the source place, you have two warehouses, and each warehouses contain 50% of your product. And you want to move this all your product to the target place. And in the target place, there is also two warehouses, and each warehouse can take 50%, can accept 50% of your product. And then we have a cost matrix here, right? And given this, distribution of the product and the cost matrix, this is a very simple example. So you can find an optimal transportation plan showing in this matrix, right? And it will give you the optimal transport cost in this problem. And here we can use this optimal transport plan as the token alignment. If you think, these are two source tokens, for example, English tokens, and these two are Swahili tokens, right? This indicates an optimal transport. So this indicates a token alignment. For example, we align the first English token with the second Swahili token. And now we can formally define this cross-lingual knowledge distillation. Suppose there is a parallel text with L tokens, the Q and Q hat. So we use this ESQI hat to represent ICE token embeddings from the student model. And then we use this ETQJ to represent J's token embedding from the teacher. And then we define our cost matrix as the cosine distance between these tokens. So we can think this cost as the energy need to move a unit mass from QI hat to QJ. And then we assign uniform probability to tokens. You can think this as equally weighted. So we assign equal weights to all of the tokens here. And so we can find a set of transportation plans, which are all the L by L matrix that satisfies this condition. And then among these transportation plans, we want to find the one that minimizes the transportation cost. Well, the transportation cost is the sum of element-wise product between the transportation plan and the cost matrix C. So we define the OT cost as the loss function, and we have the goal of the optimization here. And then we employ an existing OT solver to train our model. So here we just use this IP-OT algorithm as our OT solver. So I wouldn't go into the details. For the details, you can refer to this paper. So here's an overview of our distillation pipeline. So suppose the CoBird has shared weights between query encoder and the document encoder. We initialize the student encoder using the teacher's weights. Then we feed parallel sentences to transfer knowledge from teacher to student. Because the English token embedding contains the retrieval knowledge, the target language token embeddings will also learn the retrieval knowledge. And once trained, the student encoder can be used as a query and document encoder in the target language. Now we add back the scoring function to compute the relevant score. So in this way, we kind of use English as a bridge to improve the retrieval performance in the target language. And the most significant feature for this distillation is that it does not require any retrieval label. It only needs bytetext data, which are much easier to get than the retrieval data. And here we list other, training details of this this process. So to simulate the input of the retrieval, we randomly append, special tokens Q and D to the bytetext data. And to solve the difference of the grammar and the tokenization between languages, we append the short expressions with the mass tokens to ensure that all the bytetext tokens have the same length. And for each language, we sample up to 2 million bytetext pairs from the CIIR dataset. So here's a example for token alignment as the transportation problem, right? So given the same semantic meaning, the English and the Chinese expressions are in different token order. Actually, the Chinese is the reverse way of the English token here. So on the left is the pairwise cosine distance matrix. You can think this as the cost matrix in the previous definition, right? So just from this cost matrix, it is hard to determine the token alignment using any rule-based method, even if there's a very simple toy example here. So on the right is the optimal transportation matrix generated by the OT solver. So the transportation matrix clearly indicate how we can optimize this Chinese tokens embeddings given the English tokens embedding. And it also catches this reversed expression. As you can see, all the transportation plan are put on the reverse diagonal of the transportation matrix here. And here are some preliminary results. So we use distilled bytecode to re-rank the top 100 results produced by the BM25 and MDPR baselines. We can see that the distilled version of the bytecode improves BM25 on all languages. And for MDPR, it improves 13 out of 16 languages. Again, for this result, we haven't used any miracle training data yet. So that's all about the bytecode. So next, I will briefly introduce our cross-encoder model. So for the cross-encoder, we take the sequence classification task, and the input for the model is the query document concatenation. So after the encoding process, we feed the CLS token to the ranking header to produce a score. And we pre-fine tune this model using the M-Marco, which is the multilingual Marco dataset. So M-Marco dataset is actually a machine translated version of MS-Marco, and it has 14 languages. Here I list the comparison on the languages between M-Marco and Miracle. So the good news is that the expert already did the training on M-Marco for us, and made the model checkpoint available on Hugging Face. So, and according to their model card, it also works for other languages which are not covered by M-Marco. So for this cross-encoder pre-fine tuning step, we directly load the model using this checkpoint. So far, we have two models. One is the distilled bytecode model, and another is a pre-fine tuned cross-encoder model. Now we can take advantage of the Miracle training data to further fine-tune both models. So according to the previous study, instead of using cross-entropy loss with one negative example, we choose this localized contrastive estimation as the loss function. Basically, the idea is for each query, instead of just using one negative example, we sample a group of negative examples from the top-ranked documents. Again, we apply this loss function to both the bytecode and the cross-encoder model. So finally, we can evaluate our model on the Miracle data. So this is our evaluation pipeline. First, given the Miracle test data, we reproduce the BM25 and MDPR baseline, and then we merge them into the hybrid. And then we feed the hybrid to both, bytecode re-ranker and the cross-encoder re-ranker to get two re-ranking lists here. And then the final output is the weighted fusion of this three rank list here. So for weighted sum fusion, we grid search the best weights based on the depth set. And let's see some results. So first, for the bytecode, we compare the performance between model with and without the cross-lingual distillation. So we can see that if we skip the distillation and directly fine-tune teacher model using Miracle training data, the performance is actually lower than adding the distillation step in the middle. So this result kind of demonstrates the significance of this cross-lingual knowledge distillation. So next, we show the final result of each model, including the weighted sum of weighted sum fusion. So we can see the cross-encoder still has the advantage over the bi-encoder. We believe this is mostly due to the difference of the model architecture. And our best performance is the fusion of two neural re-rankers with the initial ranking method. So number 4 here. And now we show the average performance on different miracle splits. So we can see from the depth set to test A, the fusion shows a consistent performance. However, from test A to test B, the performance drops significantly. Since test B is an entirely new test set, so this raises the concern that we might overfit the depth set. But on the leaderboard, we jump from eighth in test A to second in test B. So this kind of prove that we may not overfit the depth set. So, but we suspect that maybe the query in the test B set are more difficult than test A. Which these just assumptions we need to which need further investigation here. So we don't have enough time to run experiments on surprise languages. We use the pre-fine-tuned model and apply them to surprise languages in a zero-shot manner, which give a pretty bad result here. Again, we don't put much effort into the surprise language. Now I would like to learn from the other groups about their approaches to the surprise languages. So far you might wonder, so what happens if we apply our bi-encoder model in an end-to-end setting, right? So far I keep talking about re-ranking. Recently, we select some languages with relatively smaller collection and apply distilled bi-encoder for an end-to-end retrieval setting. So to make a fair comparison, we didn't fine-tune the bi-encoder on the miracle training data. Here we compare the recall at 100. We can see that in general, bi-encoder model the bi-encoder model performance is better than MDPR, and the cross-lingual distillation can further improve the performance. And this trend is also true for NDCGI 10. For NDCGI 10, the distilled bi-encoder outperform all compared methods significantly. So our approach to the Miracle challenge is a two-stage retrieval system. We take the baseline from the Miracle project as the initial ranking step and build two neural re-rankers. The first model is a bi-encoder re-ranker on which we apply a cross-lingual distillation technique to transfer knowledge from English to the target language. And the second model is a cross-encoder re-ranker trained on a multilingual retrieval data generated by the neural machine translation. And then we further fine-tune both models using Miracle training data and fuse multiple rank lists to obtain the final result. So I guess that's all about my presentation. Here is the list of reference I used in this presentation. And thanks for listening. I would happy to take any questions.